So exercise 5D, solving problems using conditional probability. So first of all, what is conditional probability? So if we just look at the start of a question, we've got two face spinners, each having four faces, two spinners are thrown together, so it's pretty normal. So given at least one spinner lands on a 3, find the probability the spinners having a sum of exactly 5. So we're not just looking at spinners that are having a sum of 5, we've got a condition that at least one of them has to land on a 3. So that's the idea of conditional probability, it just makes it a little bit more complicated. So let's look at a Venn diagram to see what conditional probability is in terms of Venn diagram and see if we can get some kind of formula for it. Okay, so we've got two events, let's call them A and B. So just like the video from exercise 5C, we're going to let the intersection between A and B be X. Probability of A is going to be lowercase a and B will be lowercase b. So those little crescent shapes would be A minus X and B minus X. Okay? So using that Venn diagram, I want to calculate the probability of B given that A has happened. So that's our condition. The A has happened, and we want to find the probability of B if we know that A has happened. Okay. Now the notation for this is what I've just written there. Probability of B with a line A, that means probability of B given that A has happened. So A has already happened, so our sample space reduces down to that red circle I've just drawn. Okay, and the probability of B happening within inside that circle is that rugby ball shape where the X is. So the probability of B given that A has happened is going to be that intersection, so that's the only part in that red circle where B is happening, so X, divided by the sample space, so that'll be A minus X plus X. So the two little shapes within inside that red circle. Obviously that red circle is A, so the probability of A happening is just A. So that reduces down to just X over A. So in terms of generating a formula from this, we can say that X is the probability of B intersection A, and A we know is the probability of A. So we can rewrite this out as the probability of B given A is equal to the probability of B intersection A divided by the probability of A. Similarly, if we wanted to look at the opposite and look at the probability of A given that B has happened, so if we just reverse that, the pattern would still hold. We'd be looking at that red circle would be there instead. So we'd still be looking at the intersection divided by the circle B. So we'd end up having the probability of A intersection B divided by the probability of B. Now, the probability of B intersection A and A intersection B is the same thing, isn't it? We just want to keep, I wrote it that deliberately so it follows that same pattern as the statement on the left. So now we can rearrange these. If we take the probability of A across the left-hand side and the probability of B across the left-hand side, we can rearrange these to get formulas again for that intersection. So probability of B intersection A is the probability of B given that A has happened times probability of A. And similarly then we could do the same if we wanted probability of A intersection B. Okay, and that's known as the multiplication rule. Right, so let's see how we can apply these to a problem then. So we've got C and D are two events such as the probability of C is equal to 0.2, the probability of D is 0.6, and the probability of C given that D has happened is 0.3. Okay, so we know from our formula the probability of C given that D has happened is equal to the probability of C intersection D divided by the probability of D. Okay, or we could have just used that rearranged one I showed you in the previous slide. So therefore, 0.3 is going to be equal to the probability of C intersection D divided by 0.6. And if we take that across the other side, we've got the probability of C intersection D is equal to 0.18. And as we know, once we've worked out the intersection, then we can draw out our Venn diagram, fill in the probabilities into the different regions in the Venn diagram, and the probabilities that we want to find in the problem then are very easy to get. Okay, so if we draw that out next, so we've got a box to represent the entire set. We'll have a circle representing C and a circle representing D. Okay, so we know our intersection is 0.18. Probability of C is 0.2, so 0.2 take away 0.18 gives us 0.02, so we fill in that gap. Similarly, if we take away 0.18 from 0.6, we can get 0.42. Then if we add them up, we get 0.2 plus 0.18 is 0.2, add 0.42, it gives us 0.62. If we take that away from 1, we can say that this must be 0.38 outside. And then after we've done that, and that's D, that should be, that's the entire set. So then from that point on, once we fill in our Venn diagram, we can calculate any probabilities we want then, like we did in exercise 5C, just using that shading technique and picking up the regions that we want. Okay, so let's go back to our question we had on the first slide. So 2 first spinners, each have 4 faces numbered 1 to 4. The 2 spinners are spun together, and the sum are recorded. Given that at least one spinner lands on a 3, find the probability of the spinners indicating a sum of exactly 5. So let's let event A be at least one spinner lands on a 3, and event B can be the sum of the spinners being equal to 5. Okay? Right, so now we'll use the formula for conditional probability to work out this problem. So we've got, given that at least one spinner lands on a 3, for the probability of the spinner indicating a sum of exactly 5. So we want the probability that it's a sum of 5 given that at least one spinner lands on a 3. So that's the probability of B given A, and we know that's going to be equal to the probability of B intersection A divided by the probability of A. So we need to find the probability of it being a sum of 5 and landing on a 3, which is what the probability of B intersection A is representing. And we need the probability of A, so the probability of at least one spinner landing on a 3. The easiest way to get those probabilities is to quickly use a sample space diagram like we were in exercise 5A. Alright, so on that sample space diagram, I have just circled the numbers that land on a 3. So there's 7 of them in total. So the probability of a sum of 5 and landing on a 3 is going to be those 2 5s that I just pointed out. So we're going to have 2 over 16. So sample space is 16 possible scores. And the probability of at least one spinner landing on a 3 is going to be all of those pink circles. So it's going to be 7 over 16. So we go. And then if we do that division, we're going to have 2 over 16 divided by 7 over 16. So if we do KFC, it's a bit of C1 revision for us here. 2 over 16 multiplied by 16 over 7. So the 16's cancel, so it gives us an answer of 2 over 7. Now, alternatively, we could have got that same answer if we just used the sample space diagram actually in this question. So you can see how the two things link. We've got 7 possible numbers that give us that land on a 3. Okay, so that's how sample space is reduced, that little cross there. So there's 7 of them altogether. We've got 2 in that reduced sample space, which add up to 5. So we've got 2 over 7, which gives us that 2 over 7 as well.